Okay, we're live. Hello, everyone. Welcome to our virtual session. We are from Java User Group Bangladesh. Today, we have a special guest joining with us from all the way Germany, Saim Ahmed. He's a distributed system expert. Hi,
Okay.
Saim Bhai. How are you doing, man?
I'm doing fine, thank you. How about you? How's it going over there?
Yeah, it's fine. We are doing great today. The humidity is little up. So, how is the weather over there?
At the moment, it's 2 degrees Celsius and it's raining, so it's a bit cold.
It's a
Yes,
cool
it's
weather, right?
weather.
So I will be starting soon. So to the audience, if you want to interact with us, there is a chat section with where we are streaming on YouTube. You can ask any questions while we are speaking or while talking, discussing, and our guest will be answering when it appropriate. And let's start. Saim bhai.
Okay, then I will start sharing my slides. First, let me full screen. Screen share. Can you see it?
Yeah, perfect. Let's go ahead.
Okay, so hello everyone. Welcome to today's presentation. Today we will be talking about a few basic concepts of distributed systems. Before diving into our topic, I'll take a few minutes of your time to introduce myself very briefly. My name is Sam. I'm a Bangladeshi currently living and working in Berlin, Germany. I occasionally blog at codesword.com. I tweet at SamBD. I can also be found on LinkedIn. And if you want to reach me via email, then my email address is sam64@gmail.com. I like Java. I usually work with Java-based web application, and for the last 3 years, I've been mostly working on distributed system based on Java language and related frameworks and everything. So this is a list of today's agenda, the topic that we'll be discussing today. We will first try to understand what distributed systems are in simple terms. We will then try to understand the justification to go for them. This is the part where we will be spending most of our time today. The reason for this is that distributed systems are hard. To get them right, it is very difficult to architect them, and it's very difficult to operationally maintain them. We will see that as we become more and more distributed, it's like something bad starts happening to us, and our life gets harder and harder each and every time. That's why we should first always make sure that we are really trying to solve the problems that can be solved without going for a distributed system. We will then take a look at replication, a distributed system strategy that we can use if we want to scale reads to our database or data stores. We will then learn about gap theorem, which basically says that distributed systems are all about trade-offs, mostly. And next, we will take a look at sharding, also known as partitioning or multi-master replication, which we use if we want to scale writes to our database. Now, the description of this meetup lists some more topics in the agenda, like distributed hash tables, distributed transactions, and communication patterns in distributed systems. Unfortunately, we will not be able to cover them in this session, as the existing contents will probably take up the whole presentation time. So me and Wurokon, we both sort of like decided to hold another session where we will be exclusively discussing about them. We sincerely apologize for any inconvenience that might have caused you, but as this talk is more geared towards absolute beginners, students who are still in the university or developers who just graduated, we thought it might be best to explain the basic concepts with as much detail as possible. Yeah? Okay then, without further ado, let's get started. So a definition. A distributed system is a collection of independent computers that appears to its users as a single coherent system. Yeah. So the important keywords here is a collection of computers. They will be independent. There will be no operational dependency between them. Each of these computers will operate independently. They will also fail independently. Failure in one computer will not trigger failure in another computer. But to our end users, the whole thing appears as a single system. He doesn't have any idea that there are more than one computers serving his requests. If you pay attention to the definition, you will see that any web application is also a distributed system. Let's see an example. So this is an example architecture showing a typical web application, a bookshop. Throughout this session, we will continuously try to scale this application. And as we will see, after a certain point, we have to go for distributed systems if we want to scale beyond a certain point. This application is deployed on a machine. Let's call it application server, which communicates with the database in another machine. Let's call it the database server to retrieve and store data. User can send a request to the application server, which then returns a response to the user. This was pretty much my idea of how a web application might look like when I just graduated from my college. Yeah, I think back in 2009. Yeah, pretty simple. However, this web application is also a very, very simple example of a distributed systems. The web application and the database are in two different machines. They operate independently, and to our users, the whole system appears as a single thing, a bookshop. Let's take a look at some of the key characteristics of distributed systems. Concurrency. All the computers in a distributed system will operate at the same time. This is what we have already seen from our example architecture. Transparency. System is perceived as a whole. To our end user, it just appears as one single indivisible thing. He doesn't have any idea that there are more than one computer serving his requests. Independent failure. The computers can fail independently. They operate independently. They will also fail independently. If we consider our example, we can see that both our application server and the database server can fail independently. If the database server fails, the application server will not be able to fetch or store any data, which will probably display an error message to the end user, something like database connection timeout, or something like that. Similarly, our application server can also fail, in which case the user will see a 404 or page not found error on their browser. No global block. This basically means there will typically be no global synchronization mechanism which will synchronize operations between multiple servers or multiple machines. If you are familiar with computer architecture, you know that inside a computer there is a clock generator which continuously generates special signals known as a clock signal. CPUs execute their instructions when they receive a clock cycle. Memory input output, disk input output, etc., also synchronized with clock cycles. In a distributed environment, however, there will typically be no such thing which will generate this type of clock signals and synchronize operations between multiple computers. In short, there will be no single global synchronization mechanism in place. Now, I would not recommend anyone to go to business or to go live with the architecture that we just saw previously, because if something happens to our only application server and it fails, our users will not be able to access the bookshop. Application server can crash for many reasons. In fact, there are so many reasons that it happens very frequently in real world. Even if there are no crashes, we still have to release new features to our bookshop. And while doing that, we will have to redeploy our application to the server, which means downtime. As long as we are deploying a new release, no users will be able to access our website. We don't want that. This is why we go for this kind of architecture or this kind of setups. Rather than having a single application server, we use more than one application servers to run our application. So each of these servers are running the same copies of the application. We use another special server called a load balancer in front of these two application servers. All user requests by default go to the load balancer, which then forwards this request to one of the two application servers. If one of our instances go down, it can then use the one which is live. In that way, we have better availability. We say that our current setup has improved availability than our previous setup. Our web application has a better chance of being available to our end users. This is fairly a common structure nowadays. All modern applications sort of follow this type of structure. Now, Let's assume that our bookshop is getting more and more popular, and more users started to use it. Let's also assume that we have introduced a new feature, book review, where well-known reviewers post their reviews on different books. People are really interested to read those reviews. It's a really popular feature, trending on Twitter, people talking about it on Facebook and all, and more users are coming to our website because of it. We see a sudden surge in the number of requests coming to our bookshop. Life's good. Our website's getting popular. That's what we wanted. When a web application starts receiving more and more load, this is usually the first thing that happens. Web pages start taking more and more time to load, which basically signifies that our web application has a scaling problem. It does not scale, meaning it cannot handle a decent amount of concurrent users at the same time. Our application is popular, more and more users started using it, but it cannot handle concurrent requests above a certain threshold. We need to solve this issue urgently if we have to stay in business, because otherwise people will start to get irritated and we will lose our popularity. But then, what should I scale? Should I buy more powerful application servers with more powerful CPUs? This is sometimes also known as vertical scaling. Improve your application scale by buying more powerful hardware, more powerful CPUs, more memories. Or should I introduce more application servers? Maybe I have 2 application servers serving users' requests. Maybe I introduce 2 more or 4 more. Or should I just buy a more powerful database server? What should I do? The answer to this question is measure, measure, and measure. First, we should always try to measure and gather data from our applications. Performance data, CPU utilization data, memory usage data, query execution time, etc., etc. Based on this data, we should try to identify the performance bottleneck which is stopping us to serve more users. We should then decide our subsequent strategies based on our analysis. Distributed systems will definitely help us to scale our system to handle a large amount of concurrent reads. That's what we're trying to achieve, to handle a large amount of concurrent reads, to make more users happy so that we can serve more users at the same time. They can happily read book reviews. But before going that route, we should first make sure that we have exhausted all of our options to scale a single server, single database system. As I have already said before, and will say it again, distributed systems are hard. Make no mistake about it, they're really, really hard. So these are the focus areas that we should try to run our performance measurement on. We should try to find out whether our database is our bottleneck, whether our memory, maybe we have less memory, we need more memory. Maybe our application is CPU intensive, maybe it's performing some very, very computationally expensive operations, and that's why it needs more CPU powers. Maybe there's something wrong with that network switches. Maybe it drops packets randomly. Maybe it's just slow. Maybe there is some wrong with my disk input output. Maybe I have got a faulty network drive, which takes a really long time to perform a simple read or write operations. Maybe that's what's slowing my application down. Maybe that's why I cannot serve more users. These are some of the questions that we should try to answer first. Are my database query slow? This is usually the first question that we should ask ourselves and try to answer. Most of the time, this is where the bottleneck lies. Is our application doing some kind of calculation which requires extensive CPU power? Maybe we have a 2 GHz processor and it is not enough. Maybe we need 6 GHz processor or something like that. Does my application need more memory? Lack of memory increases disk I/O, resulting in a drop in performance. Does my application have a memory leak? Even with automatic garbage collection, it is fairly easy to create a memory leak in Java. Is garbage collection being triggered too often? We all know that garbage collection process can take a long time, resulting in drastic degradation to responsiveness. This signifies that our web application either has a memory leak or we just need more memory. Maybe we just need to increase our heap size. Faulty network switches can be buggy, resulting in network packet drops and performance degradation. If our application is calling third-party APIs and they start taking too long to finish, then it will also degrade our application performance as well. So if we can gather data on these different dimensions, then we have a very high chance of finding out the issue that is blocking us to scale. These are usually the questions that we should first try to answer before trying or going for the distributed systems. Now, these are some of the tools that really helps us to measure along these areas. New Relic, App Dynamics, Datadog, these are all paid solutions. They offer a good range of performance monitoring tools, which we can use to monitor applications. A metric is a very, very useful library for Java-based applications, which can be used to measure a wide range of performance metrics. For example, Hikari CP, a popular database connection pool library in Java, has metrics built in. So if you configure a metric server and send all the metrics data to, let's say, a Graphite database, then it will automatically tells you the average number, the average millisecond it's taking for a query to execute, total number of connections in your connections pool, total number of active connections, if there is any pending connections, so all sort of stuff. Using these metrics, we can easily measure performances across a wide range of areas. If we are using a cloud provider, say AWS, then it's highly likely that they will also offer some sort of performance monitoring tool as well. AWS, for example, offers CloudWatch. It offers some kind of performance metrics data as well. We can also use custom resource monitoring tools. There are also some open source custom resource monitoring tools available as well. Now, let's try and talk about some simple scaling strategies, the simplest ones. Yeah. First, how about we try to optimize our database queries? We will take a deeper look on this later. Maybe we could try purchasing more powerful CPUs and more memory, also known as vertical scaling, for application servers. However, it will only work if our applications are CPU and memory bound, meaning they need more CPU powers and more memory powers. If database is not a bottleneck, we could easily try adding more application server instances, also known as horizontal scaling. We just increase the number of instances. Then load balancer, rather than distributing load across 2 different application servers, the load balancer, for example, say, will distribute loads across 5 different servers. We could try using a CDN to serve static contents. A CDN, or a content delivery network, can cache static resources like JS files, CSS files, images, and etc., to decrease the load on our application servers. However, from my experience, what I've seen, most of the time, it always starts with the database. This is where all the performance problem starts. Let's talk about some simple scaling strategies that we can use to scale our database. Now, I will just simply skim through all these strategies because these are not actually the core content of our session. I'm still going through all of these points because I just want to make sure that when we decide to go for a distributed systems approach, we have already exhausted all of our approach to scale our applications. If nothing works, then we should go for a distributed system. So these are some of the simple strategies that we can use to scale our database. Single database instance. Reduce the number of queries. Pretty simple. If you reduce the number of queries, database has to perform less work per request, and it will be able to serve more concurrent users. Using indexes. Database indexes are a great way to speed up query performance. They work like magic, really. If you try to query a database, a table which doesn't have any index, let's say, and it contains, let's say, 10 million rows, and if you introduce an index and then try to run the same query, and provided that the index being used, you will see a drastic improvement in the performance. However, we should be really careful and double check the query execution plan using an explain plan statements in our production database. It's always a good idea to double check our query optimization assumptions. Like, we assume that using this index will result in increased performance in our application. If we want to verify that, we should definitely run an explain plan, which should tell us which will then tell us whether our introducing an index will improve our query speed or not. And after introducing that index, we should again verify that this index is really being used by the query optimizer that the database has. Yeah, make sure that your indexes are being used by the queries in production. That's what we just said. Indexes are like double swords. If we define one and they are not used by our queries, then they will decrease our database access performance even more. We should be really careful about this. Always remember that even if our index gets used by our query, it will still decrease the write performance no matter how tiny the reduction is, because now the database has to write the record into the table and then update a separate area, which is known as the index space, to create the new index as well. Yeah, this is very important. As we just discussed, indexes have a negative impact on write performance. So if we are creating too many indexes on write-heavy tables, then writes will start taking longer and longer to finish. And our net gain will be minus. We could always try purchasing more powerful CPUs and more memories for database servers, which is also known as vertical scaling. It's always easy, this vertical scaling. It costs more money, but still, it is a very quick and easy way to scale. And many other solutions as well. We can use something like an index view, which is like a materialized view in SQL Server, which can drastically improve your query performance if the query is hitting more than one tables and trying to join two large tables. Then using a materialized view can really improve your query performance. This materialized view in SQL Server terms is known as index view. PostgreSQL has directly support for materialized view, which can also help you reduce performance issues if your performance problem is because of joining two large tables. You could also try to denormalize your schema. Maybe you could try merging multiple tables into ones, something that really helps, because then we can avoid join operations, which usually gets costly if tables are too large. Again, we should verify all of this with explain plan. Yeah, that the join query is the one which is really slow and which is really stopping us from scaling our application. We can also try to get rid of all the constraints from our relational databases when all other options fail. I mean, you might think I'm crazy. After all, one of the primary reasons we use relational database is because of the ACID guarantee: atomicity, consistency, isolation, durability. Yeah, consistency is enforced by all the foreign key and unique key constraints and all. But trust me when I say this, trying to scale your data store by getting rid of all the foreign key constraints is still easier than trying whatever comes next. There are several companies who have scaled their systems like this. It works. We will just have to design our application a bit differently. But we'll still live in the ACID land. Well, not exactly ACID if we get rid of all the foreign key constraints, but we will still be able to do simple things like rolling back our transaction if something fails, which makes our life really easy. As we will see later that in distributed systems, that's not always an option. Okay, suppose that we have tried everything that we have discussed so far. It improved our throughput, but just not enough. Users are still complaining about the response time, and it's the database where the problem lies. It just can't simply keep up with all the concurrent read requests. If that is the case, then congratulations to us. We have a very successful business. People really like our web application. That's why they are flocking to us. They are trying to read book reviews because they really like us. We have a very successful business. Our bookshop is very successful. We're not a small business anymore. We are now a successful company as Google. Yay! No, just kidding. But really, it means we are successful enough to try out the difficult solutions. As we will see, from now on, our life will start getting more and more difficult. But that's just how it is. If we have to scale beyond this point, we have to go for distributed systems. So if you remember from our previous discussions, we were trying to scale our reads. We're trying to serve more users so that they can read book reviews, more book reviews concurrently at the same time. So that's the first thing that we should try, scale our reads. If we want to scale our reads, then this is something that we could try, read replication. Just like we introduce more than one application servers, we introduce another database server. This is what a typical replication setup looks like. This setup somewhat varies based on the particular database you are trying to use, but this is what typically the most common setup looks like. As we can see now, we have a load balancer in front of our database instances, which will distribute loads between our two database instances. One database instance is marked as master, also known as the primary instance, and the other one is usually called a slave or a secondary instance. The reason we are calling master is because this instance will be the one handling all the write requests. So whenever a write request is issued from the application server, load balancer will forward that request to the master. And all the read requests will be evenly distributed between master and slave. Let's try to understand how a read query will be executed here. So our application server issues a read request, say for a particular book review, Harry Potter and the Goblet of Fire. It will first go to our load balancer. Load balancer can then forward this request to our master, in which case the master will execute the query and return the result. But it can also decide to forward this query to the slave as well. How will it choose which instance to forward the query to will depend on your configuration and the load that each server has at any moment. So this is pretty easy to understand. Yeah, receive a read request, either forward it to master, or to slave. If master is executing too many queries at the same time, slave has a bit lesser load and forward this to slave. Otherwise, forward this to master. Now, the write requests are a bit more interesting here. Our application server issues a write request, which again goes to the load balancer. Load balancer then forwards this write request to the only master we have. Single master will receive all the writes. After executing the write query, master returns an acknowledgement to the load balancer signifying a successful execution, saying, hey, I have written the data that you have sent me. This transaction is completed. Everything's fine. Load balancer then forwards this acknowledgement to our application server. Master then issues a special command to the slave called replicate with the piece of data it just wrote. Basically, it's just telling the slave, hey, I have received a new piece of data. Please create a copy of it in yourself. Slave will then reply, finish the replication, obey the master, as it's called, master, yeah, obey the master, copy the data, and will return an acknowledgement saying, yeah, everything is good. I have written the data. I also have the copies of the data. This is what a typical write operation looks like. I would argue that our system is inconsistent. There is no guarantee that a read request will receive the most recent write for a piece of data. In fact, it might not even receive any data at all. Let's see how. Suppose that after getting the acknowledgement back from the load balancer, but before the replicate command can be issued, our application server, let's call this a client, issues a read request for the same piece of data it just wrote. It just wrote the data to the database, and for the same piece of data, it then issues another read command. Yeah. However, rather than forwarding the request to the master, load balancer now decided to forward it to the slave. It can happen. It will, in fact, it will happen very often, as master will be more busy than slave, as it not only as it has to also handle the writes as well as the reads. But the data has not been replicated yet, so slave will say, hey, I don't have this data. Load balancer will then return a not found response to our application server. Now our replicate command arrives at the slave. So our client just wrote a piece of data to our database server only to get an empty response when it queried immediately for the same piece of data. Then we say that we broke ACID. From the perspective of the client, we are using a database which no longer follows the properties of ACID. Do a fast recap of ACID. These are the properties that all transactions have when we execute them on a relational database. A here stands for atomicity. It says that any transaction executed on a database is all or nothing. If part of the transaction fails, then everything fails, and the database state is left unchanged. C stands for consistency. Now, we should be a bit careful here because consistency in the meaning of ACID, because consistency in the context of ACID has a different meaning than in a context of a distributed systems. With respect to ACID, consistency means that any transaction will bring the database from one valid state to another. That means a database will always be in a valid state. If it has a foreign key, all the data written in the database will follow the rules enforced by the foreign key. If it has uniqueness constraints, all the data written in the database will follow the constraints. Just that. I stands for isolation. This is basically a concurrency console strategy. It basically signifies how concurrent transactions are handled by the database. It says that concurrent execution of transactions will result in a system that would be obtained if transactions were executed serially. That means if two transactions runs in parallel, the net effect will be as if these transactions were executed one by one. D here stands for durability, which says that once a transaction has been committed, it will remain so. The data will persist, will be stored in a database. Even in case of database crashes, external failure, network outages, the data will be there. So in our case, we are violating durability big time. Our client just wrote a piece of data, it got an acknowledgement, and then queried for the same piece of data, but it got a not found response. From his perspective, the transaction did not happen, even though it received an acknowledgement. Our data got lost. Please note that the whole replication thing, this multiple database instances, a load balancer is totally transparent to our client. It has no idea that now there are more than one database instances handling all its read-write requests. And this is what ideally we want, because if for some reason we want to introduce a new slave because we are just receiving too many read requests, we are as successful as Google, then we have to increase the number of slaves to handle more concurrent reads. From a distributed systems perspective, we say that our system as a whole is not consistent. Again, from a distributed system perspective, consistency means a consistent system will always return the most recent write for a given piece of data. Yeah, our master just wrote a piece of data, and if our system were consistent, it should have returned the data when it issued the read query, even if the read query was forwarded to the slave. Now, inconsistent read can happen for many reasons. One reason is that the read command was issued before the replication command can reach the slave. It can also happen because of network failure. It is fairly common to lose network packets in distributed systems, as networks are the most unreliable part of the distributed systems. Even if both instances are working and up and everything, packets may still get lost. Slaves can fail. As from the definition of distributed systems, we know that computers can fail independently. So while the master is operational, slave can fail. It issued a replicate command, slave was down, it didn't receive the replicate command. But when it came back up, it has no way to know that the master sent it a replicate command while it was down. And if the application server then issues a read request and it goes to the slave, it will not find the piece of data. Yeah, so however, if a read command is issued after the replication is successful, then it is guaranteed to find the request piece of data. Master can retry the replicate command if it doesn't get a response on the first try, but we have to configure how many times it should retry. Yeah, we cannot reply indefinitely because then it will severely, drastically reduce the performance of the master. It may even block. Slave can start receiving the replicate command after it recovers from the crash. It can also happen. Master might have a list which have a record of all the successful replicate command. If it sent a successful replicate command, but it didn't get a response for slave, it records it as failed replicate command And then after a certain period of time, it retries all the failed replicate commands. It can easily do that. For such cases, for this type of situations, we say that our system is eventually consistent. It might not be consistent at a certain point of time, but after a certain period of time, it will become consistent. It is also known as a base system, basically available, soft state, eventually consistent system. So basically available indicates that the system guarantees availability, that is always there to serve read-write requests from the client. Soft state means the state of the system may change over time, even without external input. For our case, this is true. We receive a read-write request, we write the data into masters, and then we went without any external input. Master issues the replicate command to the slave, slave copies the data, and the state of the system as a whole changes from being inconsistent to consistent. Eventual consistency indicates that the system will become consistent over time, given that it does not receive any input during that time. If I receive a write request, master wrote the write request, but the application server immediately issues a delete request and goes to the master. Before it can issue the replicate command, the data will be deleted. Yeah. It will still be ultimately eventually consistent, but when we consider eventual consistency in terms of write, should not be considered when we consider eventual consistency. Now, what if we need some strong consistency guarantee? Yeah, the client writes some data, and on the next query, you should always get the same piece of data. You can do that too. As before, the client issues a write request. It goes to the load balancer. Write gets forwarded to the master. However, rather than immediately acknowledging the write, the master now issues a replicate command to the slave. After a successful replication, slave returns a positive answer. The master, upon receiving the acknowledgement, signals completion of transaction to the load balancer. Yeah, I'm finished. The load balancer then forwards this acknowledgement to the client. Any subsequent request is now guaranteed to find the piece of data. It will always be there. So our system is now strongly consistent. However, it comes at a price. In order to be strongly consistent, we will have to sacrifice availability. Yeah, that's how it is. Consider what happens when a network failure, when there's a network failure before the master can issue the replicate command. The write operation will not complete. The master, it just received the write command, it issued a replicate command, but there was a network failure, or there was a slave failure, the write command didn't propagate to the slave. What happens now? It will, of course, not acknowledge the write because it doesn't know when the slave will back up. It doesn't know when the network will back up. Let's say it marked the replicate command as failure in its transaction journal. And after 5 minutes, the slave comes back up. Now, if the master only retries the failed replicate commands, let's say after 12 hours, between this time period, from a slave coming back up to until the next 12 hours, the whole system will be inconsistent. It will not be consistent because if the server issues the read command and it goes directly to slave, it will not find the piece of data. So in order for us to be strongly consistent, we cannot acknowledge write, that the write has finished. Network failure or server failure, we cannot acknowledge our write. Yeah. For this type of situations, we say that our database system is not available from the perspective of our client because the write command will have a timeout because each database query has a timeout configured for it. It waits for a specific amount of time before this query is treated as failure. Let's say you configure your query timeout to be 5 seconds. After 5 seconds, if the database server, the application server doesn't receive a response from our database system, it will consider the query to be failed and it will throw an exception or error or something like that. This is why we say that this system as a whole is not available. It was not available to serve the write request. It just threw an error. Unfortunately, there will always be trade-offs like this. We will always have to make this type of trade-off when we go for distributed systems, which has been mathematically proven with the help of the CAP theorem. The CAP theorem says it is impossible for a distributed data store to simultaneously provide more than 2 out of the following 3 guarantees: consistency, availability, and partition tolerance. It just cannot have it all. Definition of consistency says every read receives the most recent write or an error. This is what we mean by consistency in the context of a data distributed systems. In case of our inconsistent read scenario, the read command issued after the write command was not receiving the most recent write of the data. We were simply receiving empty responses. Also consider the case where we guarantee strong consistency after sacrificing availability. If the server tries to issue read request for the same piece of data, and if the master is waiting for the first write to finish, then the read will either time out an error or throw an error, and the first write itself will time out and throw an error. The master issued a write command to the master. The application server or the client issued a write command to the master, and it couldn't successfully replicate the write command to the slave because it was down, because the network was failed or everything. A client will not receive any response at all, and after a certain time, the query will just time out and it will just throw an error. From the perspective of consistency, that is okay. A consistent system can return an error. That's what it says. Either it received the most recent write or an error. There is nothing in between. Availability. Every request receives a non-error response without guarantee that it contains the most recent write. If we recall our inconsistent read scenario, we can immediately see that it is an available system. No matter what commands we issue, write, read, we always get a response back, but our read is not guaranteed to return the most recent piece of data, the most recent write, or the most recent update for a certain piece of data, which is okay. From the perspective of an available system, this is okay. Partition tolerance. The system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes, which is true for our system. In case of a network partition, means if there's a network failure between master and slave, our application server can still communicate with our database nodes through load balancer. If it issues a read query, write query, this will either be forwarded to master or this will either be forwarded to slave. It will still communicate. So it seems like we have a choice to make. Choice between consistency, availability, and partition tolerance. However, in real life, when we go for a distributed systems, not choosing partition tolerance is not an option. There will almost always be network failures. Nodes will fail. Packet data will get lost. So network partition will definitely happen. So the choice that we have to make is between either consistency and availability. So we should either design for a consistent and partition tolerant system or an available or a partition tolerant system. In reality or in practical applications, we always go for partition tolerance. We cannot avoid that. We usually go with the availability along with partition tolerance. We want to handle more and more concurrent requests. We don't want to show an error to our end users, but we usually design for eventual consistency. Even though our system might not be consistent at any moment, after a certain point, we know that it will become consistent and we design our application based on that. But it totally depends on your use case. If you need strong consistency guarantee no matter what, then you should always design for consistency and partition tolerance. If you need to handle more users, if you don't want to show errors or like return empty response or return error response to your users, then you should go for available system, available and partition tolerant, but you really cannot have it all. However, please note that the CAP theorem only applies when there is a network partition. Otherwise, there is nothing stopping us from being both consistent and available. Only if is there a network partition, in case of a network partition, maybe because our network failed, maybe because our slave failed, then this CAP theorem comes into play. The advantage of replication is it can easily handle vast amount of concurrent reads. This is what we wanted. We can add as many slaves as we like, and our application will continue to scale. It will continue more and more concurrent requests. However, adding more slaves means it will take more time for the system to be eventually consistent when we choose availability, or increased latency or increased response time when we go for strong consistency, because now we have more slaves to issue the replicate commands to. Yeah. Configuring redundancy is very easy. Redundancy means we store duplicate copies of data. A redundant system will store more than one copies of the data. For example, both the master and the slave are storing the same piece of data. We can easily configure automatic failover, meaning in case the master node crashes, our slave can become the new master and start handling both read and write. And later, when the master recovers, it can become a slave. Or it can also become a master, depends on how you configure this system. It totally depends on your configuration, your database vendor, your database systems and all. Problems, not ACID. Yeah, that's a big problem. In ACID land, everything is very easy, pretty simple. You can easily reason about, you can easily think about them and everything. Consistency or availability, choose one. Will have to be either consistent or will have to be either available or not. We cannot have both. We can be either a consistent system or an available system, but not both. Increased operational complexity compared to a single database instance. Yeah, now we will have to configure 2 database instances instead of 1 and make sure they run smoothly in production. So these are the issues we run into when we choose to go for replication. And this make our life really difficult in real production. When you start maintaining these things, slaves can easily lag behind master by a lot. Yeah, when slaves go down and they comes back up, let's say after 5 or 6 hours, it can easily happen. Then there are lots of replication things needs to be going on. Even if you go for availability, not strong consistency, still master has to replay lots of replicate command to the slave until this whole system becomes eventually consistent. Yeah. So life is more difficult than before. Good. So even though it was not a free lunch, we were still able to scale reads. The user can see their book reviews. They are very happy. They give us 2 thumbs up. And now they start ordering books. We start making more money. Let's say this ordering stuff is really scaling. More and more users starts putting purchase order on our websites. And now we have to scale our rights as well. How do we scale rights? Easy. We just configure more than one master. Well, not that easy, but yeah, that's what we should do. We should configure more than one master to handle more than one write request at the same time. This process is also known as sharding or partitioning or multi-master replication. So, read-write operations. In order to issue either a read or write request, the client first needs to use a key, also known as the sharding key. Depending on the value of the key, it either sends the request to the cluster on the left. So the cluster, I'm calling this a single master and its related slaves and a node balancer as a single cluster. Yeah. So inside each cluster, we have one master which can handle writes, and we have some slaves configured. So we can configure automatic failover. We can also replicate this data across the slaves as well. Let's assume that the client decided to use the user ID as the key. If the user ID of the user placing the purchase order is between 1 to 100,000, it chooses the cluster on the left. If the ID value is between 100,000 to 200,000, then it chooses the cluster on the right. Each client has this user ID to IP address mapping stored inside it, maybe into some configuration file, which it uses to decide which cluster it should send the request to. So now, if we receive a purchase order from a user whose ID is 50,000, the client will choose the cluster on the left. And if we now receive a purchase order from a user with an ID value of 150,000, it will choose the cluster on the right. It should be pretty obvious at this point that each insert, update, delete, find statements issued by our client needs to specify the user ID as the key. Otherwise, we will not be able to find the correct cluster. Whatever we need to store, whatever we need to find, all statements need to explicitly specify the user ID as the sharding key. It's a big limitation of this multi-master replication, or also this sharding or partition scheme. Also notice that in this typical setup, after each write to master, the replication process that we just discussed earlier will happen within each cluster. Yeah, each master receiving the write request will then subsequently issue the replicate command to replicate data across its slaves. Now, suppose that our bookshop has a competitor. They are also getting popular. To gain competitive advantage, I started a special campaign to sell the latest release of Harry Potter and the Deathly Hallows with some attractive discounts. Each user, when placing an order, may or may not see a discount coupon with varying amount of discounts, 10%, 20%, 30%. When they accept the coupon, the discounted amount is deducted from the final price. Now, I would like to know how much money I have earned from selling that book during that campaign. This is what I am to know. I need to decide my business strategy based on this data. I've offered some discounts. I want to know whether this was effective or not, whether this increased my sales or not. Now, our orders are scattered across the clusters. Yeah. Each order contains the books that were sold with that order and the total amount the users had to pay. Since each order may or may not have a varying amount of discounts applied, so total different amounts. Each time the book was sold with a different amount. The only way to find the correct amount is to scan through each orders of each customers, checking whether that order contained that book, how much discount was applied, what was the final purchase of the book, getting the amount, and then summing it up. Yeah, this is the only way we can find the correct revenue earned from selling the book. Now, this is impossible to do in a traditional way. As we get more and more successful, we will have more and more books, and more users will start purchasing from us. If we are really successful, our total number of purchase orders stored in the system can easily exceed billions. Querying for billions of records and fetching the full result in the memory of a single server is literally impossible due to the limitation on the memory size. You simply won't have enough memory for that. It's not possible. So we cannot fetch all the data in a single application server and then perform analysis on that. This is not possible. Instead, what we will do is, instead of fetching all the data in a single server machine and applying our computations on the data, we will scatter our application across the cluster. So our application, our application server will send the computation to the cluster itself. So rather than getting the data, since we cannot get the data, it requires too much memory, we will just scatter the computation process itself across the cluster, calculate the data, or find the data that we want across each cluster, and then gather the results back. So something like this. So the application server will issue a command, something like initiate this computing procedure on this cluster, on this left cluster. Initiate this computation procedure on this right cluster. So then this computation procedure will then start on the master node. So load balancer will receive that request and then forward it to the master. So we are now trying to find the orders which contains the Harry Potter and the Deathly Hallows and the total amount that the user paid for that book in that particular order. So we calculate that results on each master. Yeah. So we calculate that results on each master, and after successful completion, each results will be something like a sum amount, which gives us the total amount that users spent to buy that book stored in the order in a particular master. So this is like a simple single individual result which we can then easily get back in our application server. So we first scattered our computation itself across our cluster where the data lies. We perform the computation on the data. We gathered the results back to our application server, because after performing the computation, the result is just a single value, or maybe two values. Number of times the book was sold, total amount. So just a simple tuple containing the number of times the book was sold and the total amounts the user paid for that book. So this tuple we can easily retrieve back to our application server from the node. Yeah. This paradigm is known as scatter gather, or more famously, MapReduce. So this approach was popularized by a famous research paper from Google, and a popular implementation is provided by the Apache Hadoop. So the idea is pretty simple. We have vast amount of data scattered across multiple clusters. We cannot put all of them in a single service memory. So instead of fetching all the data and putting them in a single server, we scatter our computation or our computational process across our cluster where the data resides. We perform our computation on the data over there, our results back to a single server. Then we combine them and voila, we have the result. It should be pretty obvious that the execution of this process is not something that an end user can initiate. The whole process, no matter how scalable that is, cannot be finished within 1 or 2 seconds. It's simply not possible. And if a query does not finish within that time, it is not suitable to be executed in a live environment. For us, that's okay, because the computation we are trying to execute are producing sort of like a report, which is for deciding business strategy and will be used by our analyst in our bookshop. Now, the advantages of sharding: can easily scale read-write to the moon. Yeah, it can really scale, no doubt about that. However, it has some fairly complicated issues. One is operationally complex. Before, we were managing one server, database server, then one master and 2 or 3 or 4 slaves. Now we are managing more than 1 clusters, more than 1 masters. Each of them has its own replica. On top of that, all queries now need to have the shard key. If we don't have the shard key, we cannot do anything. Sharding and relational database system is painful. It's really painful because our traditional database systems were not built for this type of replication or sharding process. That's one of the main reasons why NoSQL databases came to be. They are far more easier to shard or to replicate than our traditional relational database systems. We also cannot maintain referential integrity anymore. Suppose that we want to apply a unique constraints on the order table, saying that maybe 2 or 3 columns should be unique across all rows. This kind of referential integrity cannot be enforced anymore. Why? Simply because all the order rows are not residing in a single database instance anymore. They are all scattered across our cluster. So we simply cannot apply this type of referential integrity anymore. Each table must have the shard key. Yeah, pretty obvious, isn't it? The whole system relies on being able to use the sharding key. This, however, strictly limits our data model. Each entity should have the shard key. If it doesn't have the shard key, it cannot be put in a single cluster. Not suitable if most of the queries are scatter-gather. Yeah, if most of our queries are like scatter-gather, and this approach is really not suitable. Yeah, if let's say more than 40% of our queries are like this scatter-gather, for that we have to scan through the whole cluster, then this approach simply doesn't work. Yeah, because then it will take just too much time to calculate the results, and it cannot simply be used to serve requests from an end user. So when should we go for multi-master replication? When we really have to scale writes, and we can find a common key that we can use across all tables. For our bookshop, this is pretty easy, as each purchase order will have the cast user key. And if we only try to scale order, purchasing order, not the book category or the book information, it's only the purchase orders, then it's okay, because each order will have the user key anyway. And we can easily split the rows across multiple clusters. So in this case, we'll have to sort of like use hybrid situations, maybe read replicated system for scaling the reads to the book reviews, and a sharded system for scaling the high volume of purchase orders. In practical world or in real world, this is what typically people do. They sort of like use a hybrid solutions because there's no silver bullet. That simply isn't. Now, as I've previously mentioned that we also want to discuss about distributed hash tables or consistently hashed data stores, and also about distributed transactions, and a very, very light introduction to microservices. Services is usually what you get when you try to scale your organization. Let's say you started the bookshop with 10 developers. You are getting more and more popular, but not that popular that you receive a very high amount of reader rights, but still very popular. You sell like expensive books, and so you are earning more money, and now you want to increase your team members. Let's say you have increased your employees size to 100. Now, if 100 people tries to work on the same code base, it becomes very difficult because the coordination and the collaboration for even the simplest change takes too much time. In that case, what we do is we split one application into multiple smaller services, and then we deploy them in a distributed system environment, and they communicate with each other through different communication patterns. We are already over our time. So these are some additional resources that you can follow in order to learn more about the distributed systems. The first one, distributed system in one lesson, is really, really good. The person, Tim Berglund, he's a very good teacher. He explains the concepts with such ease that it is very, very easily understandable. He also recommends a reading list. It contains some of the influential articles in the distributed systems area. Then to learn more about microservices, you can read this book, Building Microservices by Sam Newman. He is also a very, very good teacher. I have the chance of attending one of his distributed microservice training sessions, and it's really nice just to see him talk. He really explains this concept with such ease that you have no trouble understanding them at all. You can also read Postgres documentation on high availability. It lists down all the different ways you can replicate a PostgreSQL databases. You can also read MongoDB application manual to see how a NoSQL data store replicates or shards itself. And there's a high scalability. It's a website which is all about scalability and distributed systems. And the last one, enterprise integration patterns, is also about distributed systems. And the guy who manages that site is sort of like a legend in the distributed systems area. So all of these are highly recommended resources. Thank you. And now it's time for questions, if you have any.
Okay, thank you. Saim, you have done a really great job explaining a lot of interesting topics. And I think we have some questions, and we can take a few. I guess we can take one or two. So I'll first go ahead with one question that is mentioned by Sajjad. Can we use client-side load balancing or use directive programming to reduce load?
Yeah, that is also another way. So usually, of course, it comes down to when everything fails. Let's say you are really successful, or you have a really highly replicated system, but still can't handle the loads. Then the last option that we have is load shedding or the back pressure. So yeah, in that case, if you reach your operational limit, that the only way to maintain the sanity of the system is to apply back pressure or load shedding. And in that case, of course, RxJava or reactive systems helps. I guess this is one of the reasons why reactive systems came to be, because in modern times, even the applications receive a very, very high amount of load. Yeah, so that definitely helps.
Okay, so we have another, it's not a question, sort of comment from Asif Hussain. In addition, those tools mentioned, Visual VM for monitoring, JVM, okay, Oracle Enterprise Manager for monitoring database query, Xtable for monitoring response time, and Drop Wizard application level monitoring. Okay, he just mentioned a few tools that we can use.
Yeah. It's true. There are lots of tools, but and it's also really interesting, all these areas, because it's performance monitoring and things are really interesting. But yeah, these are also great options as well.
Okay, so we have another question that is,
Added to that, there are APM systems which we can monitor database queries, load balances, and server performances. So it will be under a single dashboard, and we can actually make monitoring-based decision on how we configure the load balancers.
Exactly, exactly. The New Relic, App Dynamics, they're all application APM-based solutions, and they work really good. And if you use that, I mean, I highly recommend using systems like that, because it really helps us to take informed decisions, and that's the most important thing, right? We should always take informed decisions, especially when we try to go for distributed systems. But for doing that, we should always make sure that we have tried everything else. We have found the correct bottlenecks, and we have improved where improvements can be applied.
Actually, for these things, we need to analyze the patterns of web users so that we can predefine what are the things we need to monitor, and what are the failover strategies should be there, so that we can, as soon as possible, we see the error patterns, we take the actions, and do not let the server fail.
Exactly, I agree.
Well, we have Shantanu Bhai with us. I didn't mention him, but he is also with us.
It's okay.
Okay, it's nice to see you,
Nice to
Shantanu
see you
Bhai.
after a long time.
Yeah.
It has been, because I'm kind of in Dhaka on an urgent basis.
Oh, I
Oh,
see.
Yeah.
Great.
I know the reason. I know the urgency. Congratulations.
Thank you.
So we are going to congratulate Shantanu Bhai. Right. I don't know the region, but I can guess.
Keep it guessing. That's all.
Okay.
Okay, so we can take a few. Let's take two more questions. Another is from Shajjat again. Can you use document-based database to support transaction? If yes, any suggestion? What database we should use?
Document-based data transactions. Yeah. CouchDB, as far as I remember, CouchDB probably supports transactions, but if you are going for distributed systems, then I would really recommend not to think about transactions, because transactions in a distributed environment is really problematic. It will even really slow you down, and it's better try to design your system in such a way so that you don't have to consider transactions at all. If we don't consider transaction, there are several actions that we can take. For example, if we just saved something in a database, and we need to send the data through a message queue to another system. Let's say we have two different distributed systems. One is placing an order, and then once the order is saved in the database, a batch job is continuously pulling the table, sending that data over a queue to another system, which then receives the order, does whatever it takes to serve that order, and then takes care of the rest. So
okay, I have another question actually. How about CQRS? That's also a term recently used, common query and responsibility segregation.
CQRS is a really interesting way of doing things. Even if you are not going for distributed systems, even in a single monolith, it is a very, very interesting policy to follow. I believe CQRS will result in a solution which is rich in domain. Basically, this all comes from domain-driven design, and I'm a really big fan of domain-driven design. So CQRS approach really helps you to separate your applications into a part which does all the writes, and then uses events to transfer the updates to another system, which then handles all the reads. You can then individually scale the writes and individually scale the reads, but your system as a whole is of course eventually consistent, because there will be a delay when you send the update to the system which takes care of which handles all the REST requests. But yeah, CQRS systems are a really great way of application designing. If you have a complex business problem to solve, then also it makes even more sense. And also domain-driven designs are a really great fit when we try to go towards microservices, because when we decide how should we cut our single application into multiple smaller services, then having a specific bounded context helps really well to find or separate a single application into multiple applications. So yes, SQL is also a very good candidate. You can scale, read and write independently, and yeah.
Okay, so thank you. Let's
I have
take.
an ad. I have an
Okay,
ad.
sure.
I have
Go
added
ahead.
some Cassandra. I have seen based on Cassandra NoSQL DB, we can provide a transactional system on top of Cassandra. For this, we should make a separate business logic layer to actually handle the transaction for it. So I have seen in a bank where there was a transaction like 3000 plus transaction per second. It was the requirements. We handle it with a separate business logic layer, and in top of that we use message queues, JMS, simple JMS messaging, so that we can sync up, because it was the fastest option and we among different clusters. So we it can be done with Cassandra too.
So if Cassandra is sort of like if I'm not mistaken, is a distributed hash table type of database. So it's like you have a partition key, and then based on the partition key, you choose one of the servers among a cluster of servers, and then you send the right requests to the
Exactly.
server. Or if that's the case, I have not exactly used Cassandra, but I used something similar, which is Azure Table Storage. It's also a distributed hash table, so it also follows the same strategy. In that case, in that database system, you can also perform a transaction, but it is only guaranteed to be consistent within a particular partition, because each partition, data within each partition is guaranteed to reside in the same servers. When all the data are residing in the same server, then it's very easy to guarantee transactional properties and all. But if
Actually,
you're running a transaction across multiple clusters, then I don't know how it will be possible to guarantee.
Actually, for that, they used to maintain a cluster-based solution, zonal-based solution. I am talking about bank scenario, where they have a zones like a Singapore, UK, or Europe
Yeah.
zones. So what they used to do, they have all cluster under a single zone, and then they provide a transaction based on zones, so that all clusters are under same zones and they perform the similar transactions, and it can be rollback. Even it can be rollback after, let's say, a particular transaction has a warranty period, let's say 3 hours or 1 day, so it can be rolled back even after 1 day. So they used to maintain this the whole transaction scenario in a separate way, like a handling transaction as a separate application, because these are like banks, so they have money, so they these are all more valuable things, so they
Yes,
handle.
yeah, of
I
course.
think we have a related question about what we have just discussed. Shafin Mahmoud asked, "How about NoSQL in distributed system? Does it have some plus in respect of RDMMS?"
NoSQL systems?
Yeah. So he asked, "How about NoSQL? In
Yeah,
distributed
NoSQL
system."
database systems are really good they are really suitable for distributed systems. They are very easy to scale. They're very easy to use as a replication system. For example, if you consider MongoDB, MongoDB is built for sharding. Yeah, it's the document-based model. You can easily split the data across multiple tables. You don't have to worry about anything else. It has built-in support for sharding and replication. Actually, this is why all the NoSQL databases came to be in the first place, that our relational databases were not easy to scale.
Okay, perfect. I see a few comments. Those are not questions. Basically, they said hi to Saim Bhai. Good to see you, Saim Bhai. Good to see you, Shantanu Bhai. And thanks for live session, sort of. So thank you everyone who joined this our live session and who didn't able to join. Hopefully they will watch in later. And if you have more questions about this session, you still ask in our JagBD group or in the comment section of this video you're watching. So thank you, Saim Bhai, for your time. Yeah, it's really helpful for our audience, and I have learned a lot from your lecture, and I'm sure everyone would learn from your session, and we'll continue this second part after a while. Hopefully we'll schedule that and let you know, guys, when we will able to do that. Till then, have a nice day, and thank you, everyone.
You too. It's nice to see you too.
Thank you.
Okay, so So let me take another question. That's the last question. Can you please elaborate how indexing improves scalability and what sort of indexing like bitmap? Let's take this question. It's asked by Mahdi Matin.
Yeah, indexing can really help. If, for example, you are trying to query a table and you are searching for, let's say, select star from orders where order date was certain date, and you have many queries like that. You have many queries coming to your database table which tries to find orders based on a certain date, then it probably will be a good idea to get indexes on that column. Now there are many sort of indexes. The one that you mentioned, bitmap indexes, they are really great when the data doesn't have too many variations, sort of like you have like more or like yes no. In that case, bitmap indexes works really nice. But in other cases, there are also other sort of indexes which are, well, first try to get an index, and then you will see that in your query, which was taking, for example, let's say 3 seconds, 4 seconds to complete, it will be finished within less than 1 second. So indexes in that case really help. But you first have to identify the query pattern that your application is issuing to a database server, and then get indexes on the table, with using that column, and then see whether the query optimizer in production, because it totally depends on the number of rows that you have in a table. If, for example, you created the index in your test environment and a test environment has only 1 row or 5 rows, then even if you use index, the query optimizer, there's a high chance that the query optimizer will not use that index, because it just determined that scanning through the 5 rows is much faster than using the index to find the rows. So that's why you should always run your explain plan on the production database itself, and you'll actually verify that your indexes is being used on the production database by the query optimizer.
So thank you, Sam bhai. So let's. We are already late. So
Yeah.
just say call it a day. I mean, call it a night actually. So I'm not sure what time it is over there.
It's night here as well.
It's 11 p.m. here. It was great discussion, and let me tell you one thing to the audience. We are doing this bi-weekly, so there will be another session after 2 weeks. So if you just keep an eye on our group, you will able to join this live session, and you will able to ask questions directly to our experts. We are doing this from different sort of peoples from around the globe. We have some international speakers coming, joining us. So this is fun actually, and this is an opportunity. In fact, you will able to ask question directly from the experts. So this sort of opportunity doesn't come always. I mean, you'll really not get this opportunity otherwise. So I'd say it's a great opportunity, and don't miss this opportunity. So thank you, everyone. Thank you for joining us.
When will you know who is receiving the IntelliJ IDEA license?
Oh, okay. That's a good question. Let me decide now. So we have a few question. I mean, we have a few member who joined live. Let's decide from them. Okay. So we're giving away IntelliJ license who joined live, and I wanna give you the opportunity to decide. I mean, let's Samba, you decide who is going to win this license.
No, it should not be me. It really should not be me because then there's a very high chance that it will be passed. So rather than deciding, I'm deciding we do some lottery.
Okay, let's do lottery. How we are going to do that? Okay. Basically, let's go finish it. We'll announce this who is going to win this license in our group.
Okay.
So
okay.
Okay.
Bye.
Okay. Bye. Have a nice day, guys.
Have a nice day.